Okay. All right, so Dave came to me and told me that you guys wanted to get up to speed on electrical systems, basically. Mostly the motor control, because that's what applies to what you're doing. But I suggested that we start from the fundamentals because you can't really understand a motor or any other electrical system unless you understand what's going on at the base level. So we do have it laid out, everything that I think would be worthwhile for you guys to understand in electrical circuits and electrical systems, but it's way too much to cover in one day. In fact, what we're covering today in Class 1 is essentially like a Circuits 101 course. So it's a 6-month program that we're going to bring down to about an hour with some Q&A. Couple of references, and of course that's the Q&A is to fill in any gaps. We're not going to cover everything. I think this is to get you at a fundamental level of understanding so that you can work with vendors and work with customers to solve whatever problems you encounter. So the physics is where we're starting, and that is fundamentally charge. So like everything we do in mechanics is starting point is really mass. You know, how heavy are things, how much energy do they have when they're moving, and in electric circuits it's charge. I mentioned electrons here as the first point, but that's the last time I'll mention electrons, because really the concept to have in your mind is charge, and you can imagine these balls of charge as they interact with the electrical system. As opposed to gravity, mass and gravity, it's not like two things with mass will be drawn together. In electrical circuits, in electricity, we have positive and negative, which I'm sure you're all aware of. Those terms, by the way, could have been orange and blue. We could be calling things orange and blue and batteries labeled orange and blue, but plus and minus is our convention. That's all it is. It's not that one is good and other's evil. Yeah, as I mentioned, electronics, not too important for us. So if that's all to remember, opposites attract, like will repel. I think this is easier. Okay, so here we have two like that are repelling, and that's called electrical potential. An analog to this, two analogs that we can think of are a book sitting on a table. So if there was a book on the floor and I raised it up and put it on the table, I'm adding energy to that system, building potential energy and putting the book on the table. Same thing if you put your thumb over the end of a hose, you're building pressure. That's all potential. And in electrical systems, we think of that potential as voltage. And I've put a big banner here for your first introduction to electrical jargon. I tried to keep it as minimal as possible. A lot of the times you're just going to see things in quotes if it's a term that you may have not encountered or you don't really understand. But if I put this up here, jargon alert, this is something that's going to be fundamental. Anything you do in electrical systems, this is a term you need to know, and the better you understand it, the better you are communicating on these subjects. So the first one is voltage. That's electrical potential. And with this voltage, here it's a battery. That's our voltage source. That's where the voltage is stored inside. The load is on the opposite end, what the circuit's actually doing. You'll hear the term load, and that's essentially the work. Like the purpose of the circuit is to power this load. Voltage across the load is a term you might hear. So that's the battery's voltage, and in this circuit, that battery's voltage is entirely across this load, and it has that voltage drop. Say it's a 9-volt source. Now you have a 9-volt drop across this load. And again, these are all in quotes, so these are terms that are nice to know, but it's really just to communicate the idea to you. Nodes are places where the voltage is exactly the same. So on the plus terminal, that's, here we're calling it 9 volts. Minus terminal, that's 0 volts. This whole section of the circuit is 9 volts, and that's called a node. You can also hear equipotential, which is the same potential. So if there's a book and an apple sitting on the table, those are at the same potential energy levels. This is all a node, 9 volts. This part of the circuit is a node at 0 volts. And you see these arrows going through. And this is leading into the next big concept to have in electrical circuits. The arrow is pointing where the charge moves. So you've got a charge starting here, and you can just trace your finger through the circuit, and you're following where the charge moves in the circuit. And that movement of charge through a circuit is called current. So again, going back to our analogies, that's like when the book is falling off the table, then it's actually, kinetic energy in that case, or current in this case, water spraying out of the hose. It's movement. That last slide was kind of a concept of a diagram, but these are actual circuit diagram symbols. So just to take that example and kind of put it into this framework now. The voltage source, you see again the plus and minus, and it's often labeled V in a circuit. If you see V, it's almost always going to be voltage. And the units for that is volts. This is a resistor, and other than the voltage source, and we'll see some switches later, but this is the only circuit element we're going to be looking at. The only thing that exists in a circuit that we'll be looking at in this class is a resistor, and that's purely because of its simplicity. It's essentially like a wire, and it has some resistance, which is resistance to charges moving through it. That's in ohms. And the symbol is omega because it sounds like ohms, and you don't want to write a 0 in your circuit. So R, that's going to be resistor or resistance in ohms. And a light bulb is an example of that. And then our current, that's labeled I, and the units are A amps, amperes. So here's a circuit where we take that stuff that I just introduced and apply some math to it. If you know the voltage and you know the resistance, you can figure current. The way to do that is this, V equals IR. I put in tiny letters because it's not real important, that's Ohm's law. But V equals IR is the thing to keep in mind. If you want to calculate for I, so you know you've got your resistor value, you know what your 9-volt source is, and you want to find I, then a bit of algebra, and you've got I equals VR. So 9 divided by 4.5 equals 2 amps. And all of these are SI units, so it's the standard prefix, milliamperes in this case. If you want to get power for solving for watts, then that equation equals VI. P equals VI. It's just as you would imagine, 18 watts. So you'll note the R, the resistance, doesn't enter into that equation. Another important concept, which I'm sure everyone's heard, and I bet you all even have an idea in your head about which of these two is alternating current and which is direct current. That's AC and DC. It's what it sounds like. You'll see the AC on a source or in various other places. That's typically meaning that you're dealing with alternating currents. Really, there's not much to keep in mind there, but understand that your voltage level is changing very quickly in a circuit. Most of the time, that's not going to affect anything other than hooking an AC device into a DC device is just not a good idea. You can imagine things kind of go haywire. I should also say here that these weren't by accident where I put the lines meeting up. If you see 9-volt AC, that's 9 volts. Steady 9 volts, and here it goes up to 9, down to -9. That's the typical way that AC circuits are working. So, like I said, the few elements, this is, I think, the last element that we're going to see today. I should also say, if you've got questions at any time, feel free to ask them. I think it's better to answer them in the situation where your minds are. Does anyone have questions at this point before we move on? Yeah. 3 slides back, you said?
You said that, yeah, right there. That. You said that between the plus and the resistor, there's 9 volts going through that.
Yes.
And what's on the other side? Is there also not 9 volts? Doesn't it make a circle?
Okay. The question was 9 volts going through the resistor. Where is the 9 volts? Is that right?
Yeah.
So this whole section, you can think of a wire as an equipotential. That's the node in that network that we showed earlier. So this, right on the voltage source, is guaranteed 9. That's what the voltage source is doing. It's forcing that to be 9 volts. This is just a wire, so it's 9 volts all the way to where the resistor starts. So this entire section is 9 volts, and it's going to be the same deal down here. That's 0, all this is 0, all the way here. So now you've got 0 on this part of the resistor, 9 volts on this part of the resistor, and a drop of 9 volts across the resistor. And that's really the resistor being a load, taking that power. Does that answer the question?
Yeah, it does.
Okay. We were on this one. Okay, other questions? Okay, so we're introducing switches, and this one everyone is also very familiar with. I bet I don't even have to tell you, a light switch is a great example of this. It's either open, so there's no connection, or it's closed. Actually, I had some batteries here, and I realized this might demonstrate the idea. So this is an open circuit right now because there's nothing connecting the positive terminal to the negative terminal. If I close my fingers over it, I'm actually adding a great big resistor between the positive and negative. So there's a tiny amount of charge moving through my fingers. And if I take a finger off, that's an open circuit. That's an open switch. If you see stuff like this, S's, P's, T's, D's, and 3's, you don't have to memorize all those. I put them very tiny because it's not that important at this point, but this sort of code is for the different number of pulls and throws. It's like a different configuration of contacts. So maybe instead of just opening the circuit and not letting any charge to pass through, you're going to move it from here to here, and now the charge will pass through this way, kind of like a valve in a fluid system. That's what those are. If you see one of those in a switch, or you know what switch you want, just use those codes to figure it out, what you need to buy, or what the other person's talking about. In this case, we have 2 switches. So tracing our finger around, following the positive current, we just stop right there. And that means that the charge is not going to pass through. If you want to look at the V equals IR equation we had before, this is essentially an infinite resistance. It's the resistance of the air, but for a system like this, and for pretty much every system you encounter, that resistance is essentially infinite. So 9 over infinity is 0. There's 0 amps going through. In the worst case, it's an arc. It's a lightning bolt. If we close that switch, now we have the exact circuit that we saw earlier. This is, speaking to your question earlier, this is all 9 volts now up here. The switch just makes a conductor. It's just a wire crossing. And now you've got that same drop across here. It's a closed circuit because you can trace your finger all the way from positive to negative. And applying this one more time, V equals IR, so 9 divided by 4.5 is 2 amps. Close this circuit, close that switch. And now this concept of path of least resistance comes into play. Like when I was holding the battery earlier with my fingers, if I also had a wire next to my fingers, it would just ignore my fingers for the most part. A few bits of charge would pass through, but almost all of it would go through that wire. It's the leak in the bottom of the bucket. So it comes up here. It has a choice whether the charge should go through here or here. This is much less resistance, continues on to here. That's the complete circuit. Looking at this again, V divided by R, essentially 0 resistance. And you have, in an ideal circuit, I guess, you have infinite current. That's called a short circuit. As you might imagine, it's normally to be avoided. So I'm showing resistors here, but this is any sort of circuit. These concepts of parallel and series are going to come into mind, and you've probably encountered them other places, and it's the same basic idea. Here's the node at, we'll call this 9 volts, but whatever it is, the voltage source. 9 volts up here, 0 over here, which means that 9 volt is going across both of the resistors. You can follow a charge up here, it comes to this junction, and it has a choice of whether the charge is going to go through that one or that one. In a series circuit, you've got no choice. It's just going to pass through this and then pass through that. And what that means is that this is your 9 volt node, this is your 0 volts equipotential, and up here it's going to be something else, depending on what these resistors are.
So give an example of that, like if it's 9 volts.
Yeah. Okay, well, it's the simplest example. Let's say this is okay, Okay, I can't come up with the simplest math possible, but I can say something. So this is 9 volts, that's 0. This is 1 ohm, and this is 1 ohm. So these are the same resistance. So, well, I'll explain why in a moment. These are the same resistance. So here it's going to be 4.5 volts, because half the resistance is here and half is there. And the part that I was sitting on the fence about explaining is that you're actually adding the resistance together. So it's 9, and then 1 plus 1 is 2. That's 2 ohms. You can figure the current then. 9 divided by 2, 4.5 amps. And then you have that many amps crossing this resistor. So you can figure the voltage drop because you have the resistance and you have the current.
So they each have 4.5.
Yeah, if they're the same resistance. If this is, you can take it to an extreme case. So let's say this one is a tiny resistance, almost like just a plain wire. That means that there's going to be no drop across it, almost 0. And it's almost like you just had that one we showed earlier with 1 resistor and 1 here. So there's going to be very little and pretty much 9 here. 8.999 here and then 0. So all the voltage drop across the big resistor, very little across the little resistor.
Both of those have 9.
Both of these have 9, yes. So you're going to get different current through here, right? You're following the charge. This is a small resistor, we'll say, and this one's a big resistor, large resistance, I'm saying. Your charge comes up here. It finds the path of least resistance. It goes for the small resistor. Occasionally, they'll go for the big resistor. So they're both 9 volt drop across the resistors, but you're going to have much higher current because more charges are going through that path of least resistance. So there's an animation that I linked to at the last slide, which shows this stuff great. You can see circuits and you can see charges moving through it, and it's kind of like the charges are making a choice of where to go, and they usually choose path of least resistance.
So let me ask a question. So is anything that uses the current, is it a resistor, so a light bulb resistor as well?
Light bulb is a resistor.
It has an ohm rating.
Yes.
Is it, so anything that has an ohm rating, which is resistance rating, that is designated as a resistor, right?
Correct.
So anything on that circuit is a resistor.
Yes, I think everything can have resistance. There are things that aren't really resistors, like inductors, that still have a resistance. And I think there's actually a broader term that you would use for that, which is impedance. So impedance is like the class of all things that impede current flow, and then resistors are like an actual device that you say that's a resistor and it has resistance or impedance.
Okay, so if it's using the current, then it's a resistor. There's a voltage drop.
If there's a voltage drop, there's resistance. I think that's correct, yes. Pardon?
There has to be, you got voltage drop, you have to have resistance or impedance.
Right, yeah, I think there has to be an impedance. I'm just trying to think of edge cases and none come to mind. Like how you could have a voltage drop without resistance. I don't think there is one. Yeah. But to reiterate, it doesn't have to be from a resistor. It can come from other stuff. So this is a little more involved example. Does anyone take a stab at where you see parallel and series elements in here? Anyone want to take a guess at it?
You got 3 parallel resistors on the left there, but they're in series with 2 additional parallel.
Correct, exactly right. Yeah, so these 3 on the left side are all in parallel. These 2 are in parallel, and then you've got a group here that's in series with a group here. That's right, Mike. Okay, so that's all I really wanted to cover in the first lecture. There are a few concepts that are in this same ballpark of ideas, which I think are still important enough to mention, but less critical to getting through the kinds of problems you're likely to encounter. because we talked a lot about resistors, we saw a lot of resistors in the circuits today, I should mention that there are also variable resistors. So you buy a 10 ohm resistor off the shelf, 10 ohm passive resistor, and it's always going to be 10 ohms. There are ways that you can vary the resistance depending on position, light, or heat. So a position one, if you're connecting this, which is called the wiper, and one of those, that's called a rheostat. If you connect them all, that's called a potentiometer. And a rheostat might only have 2 terminals to connect wires to. An example of where we've all encountered those are light switches where you can change how bright it is. And you might do it with more complicated circuitry these days, but basically, if you turn the knob or slide the slider, what you're doing is saying, this resistor, I want to split here and only pass my electricity through this part of the resistor. You're varying the resistance that way. Photoresistor, it affects the same way, but the cause is photons, is light. So when the resistor gets hit by light, it decreases. I don't know if they make them the other way. And then thermistor, they do make both ways, where if it's hotter, there's more resistance, or if it's hotter, there's less resistance. So these are all just variable resistors. It's good to know those are out there, because I know for thermistors, for example, in our systems we use a lot because heat matters. And also this is your introduction to sensors. As you can imagine, being able to change the voltage depending on some outside thing is a basic sensor. Everything we've been talking about so far with electricity also has this aspect of magnetic fields, and that's because electromagnetism is one force. It's one physical thing. Most of the time that doesn't matter in the circuits that we do, but it's good to know that it's there, because something might be going wrong, and it's like, well, we know all the variables. If you haven't considered the magnetic fields that are also in play, then you haven't really considered everything. So anytime there's current flowing through something, there's a magnetic field being generated also. Anytime you've got a magnetic field, say like with a magnet, a rock permanent magnet, and you're moving it, that's creating electric fields. It has to be moving. And this is what it looks like. So you've got wire going through, and this sort of column of a magnetic field is going all the way along. This is interesting. You'll see it's a loop. It's the same thing as there, except for we put the wire into a loop. And what that means is that if you follow that around, the exact same thing happening here, follow around the magnetic fields, and they all line up, and you have a bunch of magnetic force all going in the same direction, which is, as you imagine, might be useful for moving things in the physical world. So it's always important, but we'll get into where it's important for us later. Lastly, like I said, this introductory circuits concepts are typically inclusive of capacitors, inductors, and transformers. And I've never encountered one since I came here. I mean, they're all over the place, but they're mostly useful if you're designing a circuit that you want to do something, or you're trying to understand what's happening in a circuit. And if you're down to understanding what the inductor is doing, then you're going to be far beyond what we're covering in this course anyway. I guess the only thing to be wary of is that capacitors hold charge. So if I put 9 volts on a capacitor and then I take the 9-volt battery away, that thing is going to be holding a 9-volt charge. And unlike a battery, it doesn't need a chemical reaction to take place to produce charge. It's just 9 volts sitting there ready to go. So people can be, injured, or you can really screw up electronics if you're discharging that where it shouldn't be. And I think that is it. That's the one I mentioned earlier. We'll have a PDF available on these. If you go here, there's probably hundreds of videos, and you'll have to bear through the sound that this guy decided to put on these, but the animations are very, very good for this. So look for, of course, you want to look for basically what we covered here in animation form.